want you to look quickly at 33. I just want us to get a little bit more practice recognizing when we have that equilibrium, that means we can set things equal to each other.
Okay, I have one question. So when it does have the equilibrium sign, it means we're doing like the same thing we just did. That's only during the intermediate in the rate law.
If you see an equilibrium in one of the steps, yes, it may mean that you're going to substitute in for an intermediate. It really depends on what your rate determining step is. If in your rate determining step, there's an intermediate, there's got to be some step that has this equilibrium where you can do a substitution. Yes. If your rate determining step doesn't have an intermediate in it, and it predicts a rate law that has reactants that are in the equation, then you're good to go and you don't have to substitute in, right? Even if you see an equilibrium somewhere else, it doesn't mean you have to do that. Okay. On 33, I'm telling you, okay, if you just have this step, okay, here's an equilibrium step. And again, what's the difference between writing F2 the way we're used to seeing it and then writing just an F symbol? Atomic versus molecular, right? Fluorine is F2, right? That's what we like. F2 is likes to be. Atomic fluorine is just a single fluorine atom. Okay. So what is this little step indicating? Well, it's indicating that the fluorine molecule actually is breaking and then coming back together, and then breaking and then coming back together, and then breaking and then coming back together. Very fast, but it's happening. Okay. So what does that mean? The rate forward equals what? The rate in reverse. That's what it means to be at equilibrium. The rates are equal. So what if I was going to give the forward reaction a K value? I would probably call it K1 without any other knowledge. I would say, well, step 1, K in the forward direction, K1. And then the reverse direction, I would call it K minus 1. So I know that the forward rate law would be equal then to what? K1 times what? F2 to the first power, right? That has to equal what? K minus 1 times single atomic F squared to the second power. Perfect. Can you do some algebra on this equation and write the concentration of just atomic fluorine? Rewrite for the concentration of atomic fluorine. Yeah.
So this is a past reaction.
Yeah.
How can we use which exponent?
You can use a coefficient from an elementary step, whether fast or slow, to write a rate law. Why do we choose the rate determining step to write the proposed rate law for the reaction we're looking at? Because the rate determining step is the one that slows everything down to the smallest value it can be. Does that mean you can't write one for any step? You can write one for any step, but which is the one that's actually the best proposal? The slowest step. Okay. So again, I want to solve for just concentration of F, right? So what do I got to do to both? What do I got to do first? I'm going to get rid of K minus 1. I'm going to divide both sides by K minus 1. But then what do I need to do? I got to get rid of the square around my concentration, right? Okay. So I wanted to know if you guys knew this. Okay, so what I have is K1 divided by K minus 1 times F2, okay, equals F squared. Yes, you guys, you can certainly just write the square root symbol, okay? So if I take the square root of both sides, then I have this equals that. Yes? Okay, that's correct. Do you guys know that this means the same thing as taking the square root? I have that and I raise this to the half power. Okay, because that means the same thing as taking the square root. So I'll write this very often, so just get used to seeing that, okay? Okay, good. Here, either way to write that is fine. I am telling you guys right now, because we got to do catalysis. Ready? You guys absolutely need to work number 34 for yourself. I have all of the solutions in the slides. That's why I left that one for you guys to work on your own, because I actually did put the solutions in the slides. Because I guarantee you're going to have a problem like this. 34. Every single bit of stuff on this page on your test on Thursday. 20 points. 20 points. Maybe. 15. 5. Hell no.
5. I can do this part. Like, that's
y'all need to practice this. Be sure you can do this. Be sure you can take data, find the orders in the rate law. Make sure you can solve for K. Make sure you can look at a mechanism. Propose a rate law for me. Tell me if that rate law is good or not. All of this. All the answers are in the slides. Y'all practice that. Be sure you can do that. Okay. I mean, that's a big problem. That unfolds a whole lot of stuff we've done this entire chapter, doesn't it? Yeah, question 1 on the test. With 6 more, show your work, and then 20 multiple choice. You know, guys, I don't know what I'm going to do yet. I haven't written it. I don't know. Maybe. Remember? I already told y'all. Y'all have shown me what you can do, so we're going to amp it up.
I did not like it.
That sucks to be you. No, just playing. And you didn't fail. Okay. Let me tell you a little bit about catalysis, and then let's be done. Okay, so we've already talked about kind of what a catalyst is, right? Catalysis. Okay. What is a catalyst? Something added that speeds up the reaction, increases the rate of the reaction. Here's some other things about a catalyst that you need to know. Okay, not necessarily these words. Hang on. A catalyst is a catalyst is reacted in one mechanism step and then produced or we might use the word regenerated. In a later step. It's the opposite of an intermediate, yeah? Intermediates get produced and then used. Catalysts get used and then regenerated. How does a catalyst speed up a reaction? What is it called when I draw this kind of diagram? Here's a XY graph. But I'm going to put energy here. And then on my on my x-axis, I'm going to just plot the extent of the reaction. This is what we talked about yesterday. This is called a reaction coordinate diagram or a reaction energy diagram, right? And what do we see? We have the energy of our reactants, okay? And then the reaction requires what to actually get going in the collision? That energy is known as the activation energy. And what does that look like on our image? Like a hill, right? That's our hill. Okay. So there's some amount of activation energy, right? That this reaction has. Can that amount of energy be changed by changing the temperature? That amount cannot be changed by changing the temperature. It just means you can pedal up the hill faster, right? Can the amount be changed by increasing the concentration? No. The amount is the same. And then it's going to come down here and I'm going to make my products, right? Because that's the easy part, right? How does a catalyst then speed up a reaction? Okay, so let's think. I said things like temperature and concentration is not about changing the size of the hill. It's about giving it more power to get up the hill, okay? Okay? Catalyst is like taking some dynamite and blowing a whole new path through the hill. A catalyst does actually change the amount of activation energy of a reaction. It's the only thing that can. It's the only thing that can change the amount of activation energy. The only thing. What if you did both things? Yeah. Even faster. You increase the temperature and use the catalyst, boom, even faster. Okay. So again, let's think. What's the phrasing? How does a catalyst speed up a reaction? Let's use this phrasing. By creating a what? An alternate. Alternate. Did I spell that right? Pathway with a lower what? Activation energy. Good job, y'all. That is what it does. That's what it does. Lower path, easier. Easier pathway, faster rate, right? Easier, faster rate. Pretty much. Pretty much. I might show you something like this. This is kind of interesting. Let's look at this. Okay, so here's this drawing, right? Reaction coordinate. Look at the one I have on the board. How many hills does this reaction have, whether I have it catalyzed or not catalyzed? 1. Okay, guess how many steps are in the proposed mechanism for either? There's only one proposed step. What if I draw this? Okay, here's okay, the reaction, right? And then I see this diagram. What's my new activation energy? Is it the first hill or the second hill? It's whatever the highest hill is the activation energy. So for this little drawing, it's this hill, right? But when you see 2 humps in this hill, how many steps are in the mechanism that was proposed? That would be proposed for this catalyzed reaction. That's a 2-step mechanism. Which step is the slow step? The first step or the second step? The first step is the slowest step. It's the biggest hill to get over, right? Right? First step is slow step.
Is there 2 steps because they have to regenerate?
Maybe. I mean, that's so dependent on.
I don't know if you got me.
No. Okay. That could be something easy to ask. I could show you some pictures and be like, which one is an image of a 2-step mechanism? Well, guys, you're looking for the one, 2 hills, stuff like that. Yeah, that question. That's what I thought y'all wanted. Okay, 20 questions of that. I don't know. Okay, one last thing. If you look at this, so you remember we were looking at the ozone layer, right? Earlier we were looking at ozone. And I said, I can't really tell you guys which is the slow step or the fast step. And then I said, oh, let's just try something anyway. And I said, because really this is not what's going on. Because when ozone turns into O2, it needs a catalyst to be doing that, y'all. It needs a catalyst to be doing that. Chlorine radicals. That's another word for just an atom, a chlorine atom, okay? Catalyzes that ozone turning into O2, okay? Just look at these 2 steps right here. Chlorine is reacted in 1 step. Yes? Oh, darn it. Hang on. What am I saying? Chlorine is reacted in 1 step, and then where do we see chlorine again? And then it's, what's the word we use talking about a reactant? I mean, talking about a catalyst. It gets regenerated in a later step. So what does that mean? Looking at this mechanism, what is Cl? That's the catalyst. Are there any intermediates here? In just the 2 steps you're looking at? I see that, and just these 2, these are not all the mechanism steps. Okay, I'm just showing you 2 of them. Come here, you. CLO and CLO. Those are intermediates, right? Can I ask you to identify in a mechanism series intermediates and if a catalyst is present? Absolutely. It should be pretty easy now. Okay. Sometimes we write catalyst in reactions in what way? In an overall reaction, we write a catalyst a lot of times above what? Yeah, above the arrow. And what is PT, guys? It's an element. This is very common, okay? A lot of times we see metals as catalysts. Like in this is the reaction that's in like our catalytic converter. Platinum turns carbon monoxide into carbon dioxide. It helps catalyze that reaction, right? What's it called when you have a metal as a catalyst and you're dealing with gases as reactants or any other different phase? That should be pretty common, easy to see as well. Hetero meaning different. If your catalyst is in a different phase and it's a heterogeneous catalyst. Okay, that's pretty easy. We're not going to talk about enzymes because I didn't get into great deal with detail with them anyway. Okay, yeah. Okay, look at these two reactions. There's one, and then there's a second one. Same reaction. Both of them, same reaction. Which one is the catalyzed one? The one with the smaller hill, right? Which one is the catalyzed one? B. Which one is the catalyzed one? They both have the same first hill, though, don't they? The second hill is a lot lower. Catalyzed. See, that's what I need you to know. That's it. That's what I need you to know. It's the what? Strangely shaped camel. Oh, it is kind of a strangely shaped camel. Very last one. I think B is also the catalyzed one. Smaller first hill. Smaller first hill. Right? Smaller first hill. Okay. Okay, that's the end. Chapter 12. Okay. Just learn it all before Thursday. No problem, guys. Okay. That second homework set that has general questions about mechanisms and then catalysis, right? The very first 5 questions on this are the Arrhenius equation that we talked about yesterday. That's the math. Everything else is like concept like we did today on that set. And then I'll get your quiz posted this afternoon, and I will make practice sets available. Yes, sorry, I had forgotten. I forgot to do that yesterday because of softball, but I'll do it today.
You going?
No.
Oh boy.
We got close. We were tied at one point. It was 4-4. Carolee hit every time she went to bat. She got on base every time. Yeah, and then she got out one time because she rounded third, and her third base coach was telling her stop, and she just went for home, and she got tagged out. And I was like, oh baby, if you're gonna run for home, you gotta be faster than that, okay? And then the other time, at the end of the game, she got out because they were running, his bases loaded, and they were running, and the hitter, she popped up, and first base caught it. And so Carolee didn't know that she needed to run back to second. She was trying to go third, and the girl who was on third had started for home and then ran back third. And so then Carolee was like, I don't know what to do. And she got tagged out again. And I was like, it's okay. It's okay. Base running, yeah, we've only really had 2 good practices. So we haven't even begun to talk about base running. So it's fine. And they put me in the dugout to be like in charge of like getting the girls in the lineup. Like, okay, you're next, get your helmet on, get your donut stuff. And Carolee was like, Mommy, you're a coach now. I was like, no, ma'am, not.